Hello students and welcome to the quick solution of All India Cast Test Series JEE Advanced 2019 Test 7A Paper 1 Code A Physics. Let's move to question number 1. In question number 1, a wedge of mass 2m is placed on a smooth horizontal surface and a solid cylinder of mass m is placed on the wedge as shown in figure. Surface between wedge and cylinder is sufficient rough to allow pure rolling. Choose the correct options. So we have to check the validity of given options. So let at the instant when the cylinder is just about to reach the ground, let its velocity in this direction is v1 with respect to ground and its velocity is v2 with respect to ground. So we can see that since there is no external force acting in the horizontal direction, so the linear momentum of the system will remain conserved in horizontal direction. So we can say that m into v1 cos theta must be equal to 2m into v2. So from this equation we can say that the ratio v1 by v2 is constant. Now if I calculate this ratio when the surface is smooth, or if I calculate the ratio when the surface is rough, then the ratio comes out to be same. So we can say that the ratio of translational kinetic energy of cylinder to the kinetic energy of wedge will be independent of surface between cylinder and wedge. So option C is correct. Option B is also correct, as we have applied the equation of conservation of linear momentum in x direction. Now we have to check the validity of option A. In option A, it is given that kinetic energy of cylinder will be more in comparison to situation when surface between cylinder and wedge is smooth. So when the surface between cylinder and wedge is rough, in that case, when the cylinder reaches to the bottommost position, it will have some velocity. Let that velocity is v1 dash, and it also have some angular velocity. Let that is omega. So at that instant, we can say that the total energy possessed by the system is, if this height is h, then at this instant, this is mgh. Now this energy mgh gets distributed in the ratio of their translational kinetic energy. But when the surface is rough, then some part of this energy mgh will go into the rotational kinetic energy of the cylinder, and the remaining part of the energy will get distributed in the ratio of their translational kinetic energy. So totally we can say that the kinetic energy of cylinder will be more in comparison to situation when surface between cylinder and wedge is smooth. So option A is also correct. So the correct answer for question number 1 are options A, B and C. Let's move to question number 2. In question number 2, a satellite revolving in an equatorial orbit appears over a certain point on the equator every 8 hours. Time period of satellite is. So we have to check the validity of given options. Let this is the planet and its equatorial plane is this, and a satellite is revolving in the equatorial orbit. Then the relative angular velocity of the satellite in the frame of the earth can be written as omega relative, and if I multiplied this by t, that is the time period, which is 8 hours, so that must be equal to 2 pi as per given question. So when I have taken the sense of rotation of the satellite from west to east, then it can be written as omega minus 2 pi by capital T, where capital T is the time period of earth, that is 24 hours, into T, which is given as 8 hours, so that must be equal to 2 pi. So if I substitute the value of omega as 2 pi by capital T, then 2 pi by capital T minus 2 pi by 24 is equal to 2 pi by 8. So if I solve this equation, then the value of T comes out to be 6 hours. So option B is correct. Now if the sense of revolving of the satellite is from east to west, then we can say that this can be written as 2 pi by capital T plus 2 pi by 24 must be equal to 2 pi by 8 in this case. So if I solve this equation, the value of t comes out to be 12 hours. So option C is also correct. So the time period of satellite depends upon the sense of revolution. So option A is also correct. So the correct answer for question number 2 are options A, B and C. Let's move to question number 3. In question number 3, a liquid of density rho is filled up to height h in a fixed cylindrical vessel. A small hole is punctured at the height x from the bottom so that range r of the liquid on the ground is maximum. So suppose when the puncture is made at this point, which is at a distance x from the bottom, then we know that in order to have the maximum range on the ground, then the value of x must be equal to h by 2. It is a standard result. So we can say that the value of x is equal to h by 2. So option A is correct and B is wrong. Now at this point, when the liquid gets ejected in this direction, the velocity of the liquid in vertical direction is 0. So the time taken by the liquid to cover the vertical distance is h by 2 is equal to half into g into t square. So from here the value of t comes out to be under root of h by g. So the maximum range R max can be written as V, that is under root of 2g into h, and the value of h is h by 2. So V into t, so under root of 2g into h by 2 into t, so multiplied by h by g. So if I solve this, it comes out to be h. So option C is also correct. So the correct answer for question number 3 are options A and C. Let's move to question number 4. In question number 4, a particle of mass m, charge q, is projected from origin with velocity v0 I cap in a region where uniform magnetic field B vector is equal to b0 minus k cap exists. If it experiences drag force equal to F vector is equal to minus k into V vector, where k is positive constant and V vector is velocity vector, then we have to check the validity of given options. So we know that in the region of magnetic field, the work done by magnetic force is 0. So whatever is the retardation, that is caused only by the drag force. So we can write the equation m into dv by dt is equal to minus k into v. So if I rearrange this equation, then it can be written as dv by v is equal to minus k by m into dt. So at t equal to 0, the velocity is v0 in the positive x direction, and at any time t, its velocity is v. So if I integrate, then we will get v is equal to v0 into e raised to the power minus k by m into t. Now we have to find out the distance traveled by a particle before its velocity becomes parallel to positive x-axis. So at time t equal to 2 pi m upon q pi, that is the time period of one revolution, at that instant its velocity becomes parallel to positive x-axis. So this v can be written as ds by dt, and on further integrating we can say that ds is equal to v0 e raised to the power minus k by m into t into dt, and that integration limit is from t equal to 0 to 2 pi m divided by qb. So this is equal to the distance traveled if I integrate this. So on further solving, it comes out to be mv0 by k into 1 minus e raised to the power minus 2 pi k divided by qb. So we can see that option A is correct and B is wrong. Since we have get the velocity in exponential form, so the speed of particle decreases exponentially. So option C is also correct. Since the speed of the particle is decreasing in nature, so the particle cannot reach the origin. So the correct answer for question number 4 are option A and C. For option D, we can say that if the speed of the particle becomes uniform in the uniform magnetic field, then it will reach the point of projection, that is origin. But since the speed is decreasing exponentially, So the particle cannot reach the origin point. So option D is wrong. So the correct answer for question number 4 are option A and C. Let's move to question number 5. In question number 5, current I0 flows in a long thin walled circular cylinder of radius r. If Br is magnetic field at distance r from axis and P is pressure on the cylindrical wall, then choose the options which are correct. So let's analyze the situation. Suppose this is a thin walled circular cylinder of radius r and the current is flowing in this sense, which is given as I0. Now if I calculate the value of the magnetic field, then we know that since the current enclosed by the cylindrical shell, inside it is 0, so magnetic field is 0. At the surface, if I applied the Ampere circuital law, then we can write B into 2 pi capital R, or if I write on the outside point, that is let at here, I am considering a cylindrical region of radius R and I am applying Ampere circuital law at this position. So I can write B into 2 pi R, that is equal to mu naught into current enclosed. So that is I naught. So we can say that from here the value of B comes out to be mu naught into I naught divided by 2 pi into small r. So if I see the variation, then variation B is correct and A is wrong. So if I see the variation of magnetic field with respect to distance r, then option B is correct and A is wrong. Now I have to find out what is the pressure on the cylindrical wall. So in order to calculate the pressure on the cylindrical wall, let I am considering a small section, this section, and this section subtend an angle delta theta at the center. So this length is r d theta. This is d theta. So if I calculate what is the value of the magnetic field at the location of the considered element of length r d theta, then the magnetic field at this location is due to this remaining portion of the cylinder. So we know that at this point the magnetic field is 0, and at this point the value of the magnetic field would be mu naught I naught divided by 2 pi capital R. So we can say that the magnetic field due to this element is same as that of the magnetic field due to the remaining portion of the cylinder at outside point. So the magnetic field due to the remaining portion is also equal to B dash is equal to mu naught I naught divided by 2 pi capital R divided by 2. So if I write the force experienced by this considered element, that will be in this direction, dF, as magnetic field will be in this direction, B. So if I find out the value of dF, then this dF comes out to be BIL. So the value of B is mu naught I naught divided by 4 pi R, that is B. I, so the current possessed by this element is I naught divided by 2 pi into delta theta. Suppose the length of this element inside is L, so this is the force. So now in order to calculate the pressure, I have to divide by the area. So divided by area, so area would be dA, so that can be written as r d theta into inside length, that is L. So that is pressure on the cylindrical wall. So if I calculate this pressure, this comes out to be mu naught I naught square divided by 8 pi square r square. So option C is also correct. So the correct answer for question number 5 are options B and C. Let's move to question number 6. In question number 6, consider the network shown in figure. At steady state, switch S is closed. Now we have to check the validity of given options. First of all, we have to analyze the situation before closing the switch S. So in that situation, I can find that the potential across this capacitor is 16 volt and the potential across this capacitor is 8 volt. Similarly, in this branch, the potential across this is 8 volt and the potential across this is 16 volt. So if I find out the initial charge on 2 microfarad capacitor, So on 2 microfarad capacitor it would be 32 microcoulomb on this side, plus 32 and minus 32. And if I calculate the charge on this capacitor, that is on 4 microfarad capacitor, so it comes out to be 4 into 8, that is 32 microcoulomb. So the charge on this capacitor as well as on this capacitor is same. Similarly, the charge on this capacitor as well as on this capacitor is same. Now when the switch S is closed and steady state is reached, in that situation we can see that this 2 and 4 are in parallel, so their equivalent is 6 microfarad. Similarly, this 4 and this 2 are in parallel, so their equivalent is 6 microfarad. So in that situation, the potential difference across this capacitor of 6 microfarad and potential difference across this capacitor of 6 microfarad is same, so that is 12 volt and 12 volt. So if the potential difference is 12 volt, so in that situation the charge on this 2 microfarad capacitor would be 2 into 12, that is 24 microcoulomb, and the charge on this 4 microfarad capacitor is 4 into 12, that is 48 microcoulomb. So if I add the charge on these two plates initially before closing the switch and after closing the switch, then I can see that initial charge is 64 microcoulomb on both the plates, and here it is 72 microcoulomb. So the charge given by the battery, if it is X, then the value of X is equal to 72 minus 64, so it comes out to be 8 microcoulomb. So option C is correct. Now in order to calculate the charge flown through the switch, if I consider these two capacitors, then initially the charge on these two capacitors, in the first situation, here the charge would be minus 32 microcoulomb and here it is plus 32 microcoulomb. This is 2 microfarad and it is 4 microfarad. When the switch S is closed, the charge on this plate would be 4 into 12, that is 48. So it is minus 48 microcoulomb, and here it is 2 into 12, that is 24 microcoulomb. So we can say that the charge which comes to this plate is minus 16. So now we can say that the additional charge which comes to this plate is minus 16, as well as the additional charge which comes to this plate is minus 8. So that finally becomes 24. So the total charge which comes to this section is minus 24 microcoulomb. Or we can say that the charge flown through the switch is 24 microcoulomb. So option A is correct and B is wrong. Now we have to find out what is the total heat loss as a result of switching. So in order to calculate, the work done by battery is equal to U final minus U initial plus heat loss. So the work done by battery is 8 microcoulomb into 24, that is the work done by battery. That is equal to UF. We have to find out what is the final potential energy stored in the system. So that is equal to, we know that the energy stored in this capacitor is half into C, that is 6, into V, that is 12 square, and similarly in this capacitor, so multiplied by 2. So that is U final minus U initial. So if I calculate the U initial, I have to find out what is the equivalent capacitance. So that is 8 by 3. So half C, that is 8 by 3, into V square, that is 24 square. So that is initial energy stored in the system, plus delta H. So if I solve this, the value of delta H comes out to be 96 microjoule. So option D is wrong. So the correct answer for question number 6 are options A and C. Let's move to question number 7.